stream is live. No viewers as of now. Maybe I have to remind in the Discord. Okay. Hi. Okay. People are slowly coming in. How is the music? How is the music? Music is good compared to voice. Excellent. Perfect. Sound is good. Great. Thank you so much. And let me try the whiteboard. That's mildly annoying. Excellent. Okay. Perfect. I think I'm probably just gonna wait for like 5 minutes. And then if nobody comes, I'll just try these prompts by myself. Okay. I think if people are here, there's 4 people here. Probably should be enough. So I think my plan was to just do Putnam prompts today. Yeah. I think I'm still gonna wait for a few more minutes, but Okay, looks like everybody left. I think I'm just gonna start on my own, I guess. So A1. So, hi Zfon. I'm just gonna try Putnam problems today. How many positive integers n satisfy the three conditions? 2020 divides n. N is less than 10 to the 2020. And I see. N is equal to like 1. Try A6 first. Okay, let me look. What is A6? Oh my goodness. Is this like some Fourier stuff? Oh god. Okay, I think I'm gonna do A1 first as a warm-up, and then we'll jump to like A6 or something, so it doesn't get boring. But I think I need to warm up. Just do A1. Should be. It looks really easy, so let me just do it. So you have A1s and B things, and you have like A plus B is less than or equal to 2020. And I guess the formula for n is like 10 to the b times 10 to the a minus 1 over 9. So you need 2020 to divide this. So 2020 is like, what is 2020? Like 10 times 202, so 20 times 101. So I guess you need like b to be at least 2. Okay, for the 20, and then you need the 101 to divide 10 to the a minus 1. And when does 101 divide 10 to the a minus 1? Well, I think you just need 4 divides a, right? This is a 10 squared plus 1. So you need b greater or equal to 2, and you need 4 divides a. Okay. Looks like that should be really easy. As long as you have 4 divides a, then this thing 101 divides it. And as long as b is at least 2, then the 20 divides. Okay, so you just have like, this is annoying now. This is like 4 divides a, so a is like 4x. And b is like 2y. So 2x plus y is less than or equal to 1010. So basically, like, we can just fix x, right? The sum x equals 1 to 5. That's 505, so 504. Y is less than or equal to, and that's just 1011 minus 2x. So in fact, this is just like or one sec, I think I did this wrong. It's just 1010 minus 2x. So x is 504, gives 2 possibilities. X equals 1 gives okay, that's our answer. Is this correct? Let me just check if this is correct. let's oh man, this is incorrect. I guess I screwed up. What did I do wrong? Oof. Oh, B doesn't have to be even. I don't know what I'm doing. Sad. So I think all this stuff is wrong. It's like 4x plus b is less than equal to 2020. So 2 less than equal to b less than equal to 2020 minus 4x. So essentially we're summing x equals 1 to, again, 504 of 2019 minus 4x. So with 504, this is like 3 plus 7 plus 11 till 2015. This is like, how many terms are there? There's 504 terms, and the average is like 1009. So it should be this. Arithmetic equals hard. Yeah. Is okay, actually, since more people are here, I'm not going to check solutions myself. Can somebody check if this is correct? For Putnam 2020 A1. And then we'll do Zfon's suggestion and jump straight to A6 after this. But it's this, can somebody just tell me if this is correct? Okay, thanks, Zfon. Okay, let's try A6 now, as per your request. Just checking the thing. Okay. Yeah, okay, let's try A6. So, let's scroll down to A6. Okay. And let's create more space here. Oh my, what the hell was that? Okay, let's... So if I say, oh no. Maybe let's like... Okay, there we go. Okay, excellent. A6. This looks really hard, not gonna lie. I don't remember how Fourier analysis works, so this might be very hard. But I guess let's give it a shot. N plus 1/2 minus little n for n plus 1 times 2n plus 1 of sine 2n plus 1x. Oh my goodness. So now overall, basically you want to find the best upper bound you can for this function for all capital N and for all x. So best upper bound, find best upper bound. Okay. Okay, man, I'm just gonna say this looks very hard. Yeah, it's not Fourier. I mean, I'm just saying like you're adding some signs, right? So it looks like Fourier. That's all I'm saying. Yeah, I mean, I bet like what we're gonna do is we're just gonna write this thing, this guy here, as this, right? And then you just take the imaginary part, and then you sum a arithmetic geometric series. Is it even doable? Let's say I do it like this, right? Then is this even doable? Like, let's think. Uh, One sec. Okay, I'm back. So does this kind of approach work, or we just do it like a geometric series? Um, this seems very difficult. Because this thing, it's like some constant. It's like, this is really bad, right? This is not doable. We can't find a closed form for this, I don't think. Yeah, I'm very doubtful that this is straight can find a closed form. Wait, Zfon, are you still, if you're still there, do you have like, do you agree with this, or do you think it's possible to find a closed form? I'm very doubtful. Maybe like to find the max, you have to do like some actual, just like graphical, like not graphical, but just like inequality analysis on these signs and stuff. Maybe. Yeah. I mean, okay, like if we like go back to the original thing. Yeah, sure. I'm like a little confused. Oh, I see. Like, okay, so okay, here's the interesting thing. If you replace sine with cosine, then maximizing f and x is trivial because you just take x equals 0, and this is obviously a maximum. If you replace sine with cosine. Right? And now if we like take x equals pi over 2, then this thing is an alternating summation plus minus of this series. That's like the best you can do, I think. So if you view this thing as like a series with these signs as coefficients, you can sort of like, yeah. How does this series grow? It's like, n equals 0, this thing is just like about 2, and then as n keeps growing, this thing becomes smaller and smaller, eventually approaching 1 over n squared. N equals 0, n equals 1. Wait, here's an idea. Here's an idea. Let's say I define a little n to be this quantity, right? This thing drops rapidly in little n. Not rapidly, but like pretty fast, it feels like. In fact, I think we should do a concrete example. Let's just do a concrete example. Let's take n equals capital, let's take capital N equals 3. So A0 is what? A0 is 7 over 4. No, you think this kind of thing is not correct? You think you should just bash with algebra and just find the explicit form? I still want to try this. Like, do you see my approach here? Like, I'm trying to do like a smoothing argument to smooth to x equals pi over 2, and somehow claim x equals pi over 2 is just the maximum. In particular, for example, if you have like a0, if you somehow showed that like a0 is bigger than a1 plus a2 plus an, or plus a capital N, which might or might not be true, then you're done by smoothing to x equals pi over 2. Oh, you're lagging. Oh, that's... Oh, but you claim you can just find this series. I still want to try this approach. I just want to see how these coefficients grow in size. Yeah, refresh, go ahead. And then I'm going to sort of then go from there. So 7 minus, so that's 5. 5 over 4 times 3. In fact, I don't know why the capital N plus 1 is even here. Let's like pull it out. It's completely unnecessary. It's just over 2n plus 1. A0 equals 7. A1 equals 3, so 7 minus 2 is 5 over 3. A2 equals 3 over 5. And A3 equals 1 over 7. Yeah, so... Okay, so one of those is geometric series. Oh, yeah. So you're saying you have sum of x to the 2n plus 1 over 2n plus 1, and you're going to compute that by integration? Right, like integrating a generating function. That would work, right? The minus 1 plus is a geometric series. Yeah, all right. Yeah. You take like you end up integrating something, right? Like if you take a derivative, it becomes nice. Yeah, I see that. I bet that works. Well, I just wanted to still see if this approach somehow makes this obvious. Actually, what I'm saying is completely wrong. This doesn't even make any sense. My bad. Or maybe it does. No, it doesn't. It doesn't make any sense. What am I even talking about? Okay, so you're just going to just evaluate it. Okay, fine. This is equal to -1. Dang, I don't like this. This would be so bad if this is the solution. Don't you have to integrate some nasty generating function though? How are you even going to do that? It's going to end up being so bad. Right? Wait, Zfun, don't you have to integrate some like thing, some like generating function, which is like the sum of z to the 2n plus 1? Doesn't seem very pleasant at all. By setting derivative to 0? Wait, no, like, no, like, but aren't you going to find a closed form expression for fn? Or something? Also note that this function is a critical point at pi over 2. Yeah. No, but note that this function derivative is 0 at pi over 2. I'm like pretty sure pi over 2 is the answer, low key. Or like x equals pi over 2 is the maximum. Do you agree? No, but I still don't think you can find a closed form for fn prime. It's pretty bad, right? Like, yes, you gave me a method which could theoretically do it, which is a generating function idea, but like, I'm still not convinced this is possible. Yeah, but don't you have to integrate one of them? Like, isn't one of them like, I'll write it right here, like sum of z to the 2n plus 1 over 2 to the n 2n plus 1? Don't you have to evaluate this? No, I know, but don't you have to evaluate this summation right here? How are you going to evaluate this? Like, yes, this is the integral of like, right? Just the integral of like, wait, but don't you want to integrate it? No, but if you do fn prime, then all that big... Oh, smart. Yeah. Okay. I'm just being really stupid. You're right. Yeah, you're absolutely right, of course. It's just arithmetic geometric series. Okay. That's so lame. I'm disappointed. Let me like try this again. Like, How do you like select stuff? Yeah, Putnam is lame, of course. Okay, let's just so for everybody, like let's just do it. Let me just do it on the board here, even though. So fn prime of x Oh, sad. Okay, goodbye. So this is like... So we're essentially just computing the derivative of the function. And then minus... well, let's just take times 2. 2n plus 1 minus 2n. Or okay, maybe I want to just do this differently. Yeah, thanks. I'm just gonna do this differently. Like is equal to 2 over n plus 1 2n plus 2 minus 2n plus 1 times cosine which is, oh my god, which is equal to like if we let z equals e to the ix, then we just take the real part. We're just implicitly taking the real part. Let's make this. No, never mind. Okay, and this thing, it's just z times z to the 2n minus 1 over z squared minus 1. No, plus 2 there maybe. Write that again. Right, so z times, yeah, this looks right to me. And this is equal to like z times sum n equals 0 to n of 2n plus 1 z to the 2n, which is equal to z times the derivative is equal to z, oh my god, z times the derivative of what we had before. So this is pretty unpleasant. Yeah. I mean, even when the dust settles, how is this going to help? We're just going to get some polynomial in z of degree n, which is to be set to 0. Excuse me. And then I still think we have to just show x equals pi over 2 is the optimum manually. Like, this will imply x equals pi over 2 is an optimum, but then you get a bunch of other. You get, like, order O of n. You get O of n extrema. But then you have to verify all those manually, which is really bad. You still have to do the same sort of smoothing type of thing. So if we just go back to directly trying to smooth, let's scroll up. So like right here, we have these AIs and we're essentially like multiplying them by cosines and stuff, or sines in this case. So yeah. Yeah, somehow I still think that we can just show directly x is smaller than this thing. The coefficient on the 7 will be a lot smaller, which we don't like. But then the coefficient on 5/3 will be a little bit bigger. So I think the point is that, like, even if the coefficient on 7 decreases by epsilon, then if all the other coefficients increase by, but the problem is that now, like, if you're 7 times sine, just sine x, I think it's pretty clear that x equals pi over 2 is a local optimum. But if you go to anything else, then the coefficient on 7 is a lot smaller. But the coefficient on other things are potentially a lot bigger. I really don't want to do the geometric series thing. Just so bad. To manually find all the optimums and then check all of them and check that their smoothing is like... How bad would it be? It's like... Yeah, this is really bad if we try to do... I don't think you can even find the roots. So I think you have to argue like this. So let's like try to argue this again. So let's again, I'm assuming n is odd just for simplicity. So you have like a0 equals 11, a1 equals like, what was it, like 9/3? 9/3, a2 equals like 7/5. Yeah. And then we have like a0 sine x plus a1 sine 3x plus a2 sine 5x somehow you want to minimize this expression. Or maximize, my bad. In particular, I want to show that this is equal to less than equal to f11 of pi over 2. Yeah, so how would we do this? So if sine x is sufficiently like less than 1, I think we have to use size non-trivially of these coefficients. So if sine x is less than equal to, yeah, I know. Let's just say something along the lines of like, let's say it's less than equal to 10/11. Or not 10/11. Maybe, hopefully, this is not going to be good enough. Let's say sine of x is, let's just be extreme and just say sine of x is less than equal to 1/2. Then f11 of x is bounded above by a0/2 plus a1 plus a5. Or plus a5. Also, this is not f11, this is f5. This is n equals 5. And I bet that this is less than equal to a0 minus a1 plus a2. Or 3 pi over 2, yeah. And the reason is that this thing like, when is this true? This is true if and only if a0 Is this true? 2a1 plus 2a3 plus 2a5 minus a2 minus a4. That's about like 6 plus 8 plus 9, 8. Yeah, this is not good enough. We need like 1/3 or something here. Damn. So sine of x is potentially like, yeah, doesn't seem very good. Sine is something else then. Yeah, I'm not really sure what to do for this. I'm gonna be back in a sec, but yeah. Hi, I'm back. Okay. I think this approach is bad. Let's just go back to the derivative thing. Maybe it's not actually as bad as I think. So what we end up getting, I'll write it down here, is that fn prime of x equals 2 over n plus 1 times two n plus 2 z and then minus simply z okay. So maybe we just put our heads down and just evaluate this. So I guess the derivative would be like which would be like z, and then how does this work? It's like u prime b, so u prime v minus v prime u over which is so the u prime b means the degree of this 2n plus 2 is 2n plus 4. Yeah, 2n plus 4 is correct. Plus 2z squared. Oh man. This is 2n plus 1 z to the 2n plus 4 plus z squared plus 1 Thankfully, z squared minus 1 is a factor on the top, because if you plug in z squared equals 1, you get 2n plus 1 minus 2n plus 3. Yeah, so z squared minus 1 is a factor on the top. But exactly what the factor is, how would you compute that? It's not very clear. Perhaps this is the... Well, obviously z squared minus 1 is a factor on the top. What am I even talking about? It's obviously a polynomial. We don't want to factor that. So I guess what this means is that let me scroll down. Times z to the 2n plus 3 minus z over z squared minus 1. Or let me instead Let me factor a z out. And then say this is now minus this whole behemoth. Is equal to 2z z to the 2n plus 2 minus 1 z squared minus 1 minus plus z squared plus 1. Oh, I have to. Which is equal to times, now the z to the 2n plus 4 component is just z to the 2n plus 4. The z to the 2n plus 2 factor is what? Well, it's minus, so it'll be minus 4n plus 5. The z squared factor will be minus 2n minus 2. Man, this is so bad. This is so ridiculously bad. My goodness. And you need the real part of this to be equal to 0. Oh no. Why is this so bad? Can we verify this is correct by verifying that z squared? Clearly something is wrong here. This should have been a plus. I see. All these signs are wrong. So this is actually z to the 2n plus 2 is minus 2n plus 2, so it's just 1. Because it's minus 2n plus 2 plus 2n plus 3. And the z squared coefficient is minus 2n plus 2 minus 2n minus 3. This is plus 2n plus 1. Does this work? Well, it certainly satisfies it. Z squared minus 1 divides it. So that's a good test. So how the hell do you find out what the real part of this is, since you have a z over z squared minus 1? This is so bad. You need the real part of this to be 0. So you need to be negative of its own conjugate. So you want to set this to 0, so it needs to be negative of its own conjugate. Right? So equal to negative of its own conjugate for this thing to be real part to be 0. So somehow you want like to be equal to -1 times its conjugate. So conjugate will be 1 over z, but then you get 1 over z squared minus 1, so you get, I think you would get z cubed over and now you essentially would get a times now essentially just 1 plus z squared z to the 2n plus 2 so now the z squared minus 1 squared cancels out, thankfully. Then you end up getting z to the 2n plus 1. So you end up getting that like z to the 2n plus 2 y'all can't see this. Is equal to 1 plus z squared minus... I think I've almost certainly made a computational mistake. There's just probability of 1 with that, so all this work is anyways wasted. I guess like stuff Loki. Oh, this is actually pretty good. So you get like minus z to the 4n plus 6 minus z to the 4n plus 4 plus 2n plus 3 z to the 2n plus 4 minus 2n plus 1 z to the 2n plus 2 and this is actually not that bad because all the things corresponding to n cancels out. Plus z to plus 2z to the 2n plus 4 okay, and just to confirm, yeah, epic troll, yes, clearly. I think I'm pretty close to being done though. It doesn't look that bad because it looks, it should be z squared minus 1 should cancel out, right? Z squared minus 1 cancels out, and I bet z squared minus 1 squared has to factor out as well. Oh, but that's the entire point. It's going to be pretty bad. So this thing is 0. Can this be factored easily? Plus 1. Yeah, z squared plus 1 factors out pretty simply, right? So this is like minus z to the 4n plus 4 z squared plus 1 Whoa. 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 This is insane. This is just insane. After all this computation, we finally get... Oh my god, my mind is literally blown. This means I didn't make any mistakes, because there's no way it could be this nice. This is right. Wow. Insane. This is just brutal. This is just brutal. Oh my goodness. Oh my god, this is just brutal. Ridiculously brutal. Okay. Okay, we're not done yet. There's still a lot left. So that means that local optimums are going to be at z equals plus minus I and z equals 2n plus 2th roots of unity. Are local extrema of f. And here, obviously, z is equal to e to the ix. But what this means is that I want the local extrema to be at z equals I. That's the only one I care about. And 2n plus 2th roots of unity. Okay. So at a 2n plus 2th root of unity, we're still not done. Like, incredibly, even after we prove that n to infinity f and x an integral. Yes, probably. It is. It should be. It is. I don't see how that helps, though. Because you still have to show that, you still have to find the local maximum of f and x for all n. Maybe that'll be there once we prove that, but we still need to prove that x equals pi over 2 is the actual minimum, or maximum, is the actual extremum for each specific value of capital N. So there is still work left to be done. We're still nowhere near done. We've just shown that, yeah, it's still not done. Can I easily just eliminate the other two and just show... Oh, you can't even see what I wrote after this. Which means that the extremum must be at x equals plus minus pi over 2, or x is equal to 2 pi times k over 2n plus 2 for 0 less than equal to k less than equal to 2n plus 2. And k over n plus 1. My god. Still, how do we show that these are not optimums? This is still really... still really bad. How do we show the other guys are not optimums? You can't plug them in and compute. That's just... Is that what you're supposed to do? 2 pi over 2n plus 2. And then 2 pi times 3 over 2n plus 2. What? So even after we computed the derivative, roots, we found the local extremums, yet somehow this problem is still impossible. Obviously. And obviously we only have to look at 0 between x's. Because if we look at the other sign, all the signs are negative. So it's obviously, we just need to look at this for between 0 and n plus 1. So there's these rational points, rational angles along the semicircle, which are the possible extremums. But like x equals pi over 2 is really obviously like the maximum, the best one, but how do you show that? The sign of the top one of the sign of the largest term is k equals 0, so, or n equals 0 is a sign of this. This is still how I still don't see how you solve the problem, even when we did all this algebra to compute that these are the extremums. I still don't see how to finish. I can't believe this. I literally cannot believe this is the problem. It's just terrible, terrible stuff. My God. So we found the potential extremums, yet we're still dead in the water because I have no idea how to evaluate f sub n at a root of unity. What? I bet some Fourier analysis thing here is like why this works. Like fn of some rational multiple of pi somehow is guaranteed to be bad or something, guaranteed to be small. Oh my God. What to integrate that? Plug in. This is brutal. How do you do anything from here? I found the extremums, and I can't even plug them in nicely. I legit can't even plug them in and get any information. I'm just screwed. I have no idea what to do. But I need to now finish this problem because I've already started. What? What do you do from here? Plug in pi over capital N plus 1. And then what? The sign? Okay, it's super small, so like size would get rid of that case. But what if you take k to be really close to 1/2 of n plus 1? I guess you can deal with that case as well. See, now we're back to square 0. Like, we have to figure out how f looks on like an entire semicircle, like densely anyways. So the whole thing of finding the extremums is wasted. Not wasted, but like any analysis we do here, we might as well have done for regular x, any x from 0 to pi. We haven't really gained much by doing this. I guess like yeah, what can we say? What the hell can we even say? I'm legitimately baffled. I'm so confused. Anybody have any ideas? How do you find... I'm convinced the global maximum is pi over 2. There's no way it's not pi over 2. But how do you show that? Like, we know now the function... This is like 0, this is pi over 2. Then like... The function looks something like... I don't know, this drawing is terrible, but like... Function looks like that, something. But how do I know that this one is the highest? Okay, actually... Okay, I'm like desperate right now, so I'm going to like do something really bad. Like, it's going to be a whole bunch more computation. But like, if I go now back... If I now go back to... Can I somehow just... Because I know z to the 2n plus 2 is equal to 1, which makes potentially life a lot easier. But then the question still becomes, how do I evaluate... How do I evaluate this sum? Even when z is a capital 2n plus 2th root of unity. Still extremely unclear how to evaluate this sum. And this integral seems pretty intractable to me. I mean, obviously integral 1 over z squared minus 1 is tractable. But integral z to the sum power over z squared minus 1, maybe it is. You just do the same cotangent trick. Like... Not cotangent, like... How do you evaluate integral 1 over x squared minus 1 dx in like normal math? Or can we just like... Okay, let's scroll down. So let's go back to this. So we have x is equal to... Okay, so z is equal to e to the I x, z to the 2n plus 2 equals 1. Now can we evaluate fn of x using our geometric series type method? So it's again 1 over 2n plus 1 2n plus 1 minus 2n over 2n plus 1, which again, as we saw, is plus, so it's minus 1 plus So it's like so I guess we know this term is 0, right? Because z to the 2n plus 1, this is evaluates to like z times z to the 2n plus 2 minus 1 over z squared minus 1. And I guess we can assume z is not equal to pi over 2. This term evaluates to 0. So we're just concerned now with this term. This is equal to n plus... That's in fact, it's just straight up equal to the 2n plus 2 that cancels out. When z and z is equal to e to the pi I k over n plus 1. Okay, this isn't that bad, potentially. So this is now the integral of this. Okay, I need to scroll down. That's what that is equal to. But how do I evaluate this integral? I'm going to use a different variable because it's not the same z. Let's just call it x. How does one evaluate this integral? X to the n. So can I write this as a partial fraction? Something over x minus 1 plus something over x plus 1? Ax plus bx. Oh, like, yeah, what if you have something like this? Technically would give you sort of what you wanted, right? Because this gives you x to 2n plus 2 over x squared minus 1. So I guess the question now becomes, can you evaluate integral of and the answer is yes, you can evaluate this integral. Okay, so I guess we're in business. This is now like the integral of, if I let y equals x minus 1, this is the integral of y plus 1 so there's some log y term, but then there's a bunch of binomials. But this is still bad, right? This is still bad. This is still like... This doesn't really help. This is just going back to what we had before. It's just the same problem. Need to somehow evaluate this in the form of z is nice. Just the real part of this. just the real part of this. Real part. Can we show that that's bounded by something? That's all we need, right? In the pi over 2 case, what does this go to? This goes to like in the pi over 2 case, this grows approximately like 1 over 2n plus 1. This grows like 1. This is constant order. So we can't even show a bound on this thing. This thing right here. Oh, we just care about the imaginary part of this. My bad, never mind. But still. I'll be back in just a sec. I'm back. Okay. Still don't know how to evaluate this when z is, yeah, how to bound it. I don't see how you would bound it without evaluating it. Oh my god. Wow. Getting destroyed by this problem. Let me just check something. Okay. It literally suffices to show that the sum no imaginary part. So z is one, 3, so we have over n plus 1, so you get 1, 3, all the way to n plus 1. So you have all these roots of unity, but they're being summed with different weights. With decreasing weight. Oh my god, I'm being really stupid. Am I? This is just like some Taylor expansion for log type of thing. Right. No, but... Oh. Right. If we know that z to the 2n plus 2 is equal to 1... Oh my god, can we sort of cheese some really crazy kind of manipulation here? Oh, I would be happy if we could do that. Okay, let me write some stuff. I have an idea. So, as you know, log of 1 plus epsilon is what? Epsilon. Oh my god, is it minus epsilon squared over 2 or plus epsilon squared over 2? I don't even remember this. Well, I bet it's minus, right? The second derivative, log is not convex, so minus epsilon squared over 2. Okay, so on. And log 1 minus epsilon is the exact same thing, except all signs are negative. So in theory, if we subtract these two, then 1/2 has the exact Taylor series that we want. Okay, let me scroll down. Okay, but we want to evaluate this. So I think I have a trick for this. So z to the point is that we want to evaluate this, but z to the 2n plus 2 is equal to 1, and we want to just evaluate this out to from term, so this is called term 0, term 1, term 2, term 3. We want to evaluate this out to n equals 0, capital N. To term capital N. So the idea is that we can plug in epsilon equals rz, where r is very much less than 1. And z is still this root of unity. And now this thing is equal to epsilon, but then you now will have epsilon plus now the capital N plus 1th term. Like the point is that now like the n plus 1th term here is 2n plus 3, and z to the 2n plus 3 equals z. So it's like, oh, this is bad. No, it's fine. It's like z times r plus r to the 2n plus 3 plus r times r to the 1 plus sort of like so instead it's equal to like zr times 1 plus this times this geometric series, which is essentially 1 plus r to the 2n plus 2 plus so on, which is essentially just like 1 over 1 minus r to the 2n plus 2. And the same with the next term. It'll be z cubed r cubed over 3 times the same factor. I have to scroll down. So what we're saying essentially is that this is equal to 1 over 1 minus r to the 2n plus 2 times the exact sum that we want. And if we define now like g of r to be the sum modified by over my bad. Straight up just times gr. So now what we have is that 1/2 log 1 plus and I want g of 1. This might just be so BS that nobody even knows. This is true if r is less than 1. When does the log Taylor series converge? So what we're saying is that z to the 2n plus 2 is 1. Then I think this is true for any r less than 1, I think. Now log of a complex number is still kind of a iffy. Oh, scroll down. Log of a complex number is kind of a iffy topic, but it should be like log of r e to the I theta is just like log r plus I theta plus I theta. I still think this makes sense. So I think this implies that limit is equal to 0. So I think this implies, if I'm not mistaken, what this shows is that fn at essentially pi k over n plus 1 as long as k is not equal to 0, n plus 1, or n plus 1 over 2. Otherwise the log thing breaks. Because, for example, you would get like 1 plus I over 1 minus I, which is equal to maybe this is actually not that bad. Is it true that when n is odd, this thing is 0? No, it's not true. Took log of these small things. Yeah, like, I think the other way to phrase this is like, let's say you go back up to this series. Or like, let me just write it again. Like, what I'm essentially saying is I'm trying to compute if and then what I'm saying is that this is essentially like 1/2 of, if I just compute this log and subtract this log, but times infinity. Or, my bad, like infinity times this. So this thing must be 0. Maybe this just means the series can't converge and I'm just being bad. No, but if I then do modify with the r, right, then it does make sense. Yeah, I think this is right. If you want to be precise, you can define log with branch cuts and stuff, and you can define in the complex plane some complex analysis thing. Anyways, but then the point here is then that x equals pi over 2 is the max. So x equals pi over 2 is the max, which means that the sequence is like two n plus 1 minus 2n, so n equals 0. That's like 2n plus 1 minus this sort of alternating sum. And now how do you bound this? Oh. So like okay, like let's just be more careful. We're very close to being done now, I think. I'm still not convinced by my log argument. I need a branch cut at pi I, right? And then I'm considering 1 plus rz, so I'm considering a log here and a log right above the complex plane, and 1 minus rz. And I'm subtracting those two logs. Power series is valid, I suppose. I don't see why the argument is wrong. It's probably right, I guess. No, but doesn't that then imply that any series then is 0? My argument is BS, right? Because if you have Yeah, my argument is wrong. Oops. My argument makes no sense. Yeah, my argument makes no sense, unfortunately. So my thing about pi over 2 being the max is wrong. But it can be salvaged? No, it can't. It can't be salvaged. Yeah, maybe it can. Yeah, I'm pretty dead with this problem. Maybe I should just figure out how to like just do this pi over 2 case, and then I can't really do the other part. It's too hard. That whole log thing was all wrong, unfortunately. I don't know what I was doing there. Minus 1 to the n of like n plus 1 minus yeah, so that the whole thing, so that each f of capital N x is like bounded by 1. Otherwise, the maximum would just keep growing and growing. So they want to like make you analyze all capital N at once. Do you see? Like, otherwise, f of n capital pi over 2 would be growing on the order, would be growing with n. Yeah, just if you read the problem statement, then otherwise it wouldn't make sense. No. But we are essentially solving for each n. That's how we're doing it. But I still technically haven't really solved it. And it's even to 0, and this thing is like, yep, read, as Luke likes to say, right? What is this? I'm so dead right now. I don't even feel like doing this. But what is alternating sum of powers of like 1/3, 1 minus 1/3 plus 1/5, so on? This is like some well-known series, right? Do you remember what this is? I forgot what this is. Okay, but anyways, if n is even, if capital N is odd, then this is 0, the second term, and then the first term, it ends on a minus, and then the next time you're gonna get, it ends on a minus, yeah. So it's less than or equal to the final series sum. Yeah, and then if this is plus, then I think this is very easy to show. This is always less than or equal to n equals 0. And in fact approaches this. So this is my bad. So I think the answer is just this. We can very easily show this. I forgot what this series is. But yeah, that's the answer to the problem. I'm going to read the solution now, because I think this problem is really hard. How did they do it? Wait, what? Which is non-negative. Man, did I get trolled? Oh wow. That's actually crazy. Okay, by the way, this series is... Oh my god, wow, okay. I sort of see what's going on here. The fundamental issue is that, like... So my answer is right, obviously, because it's pretty obvious that that's the answer, but to prove it... This graph is actually wrong that I drew right here, this wavy graph. It actually... It ends up looking somehow, it ends up looking more like... It ends up looking different. And if you actually compute the derivative and write it out... Wow, okay. I'm now like... This problem is actually kind of nice. Fn prime x is all this. So this is the expression that I'm caring about. This was apparently simplifiable, is the point. And let's see, can we see that immediately? Is right. I think I sort of missed something very obvious here. Okay. So after reading the solution, okay. This is what we had. This was the derivative. And now this thing factors. I think. Maybe I'm wrong here, what I'm doing. Okay, maybe this actually doesn't make sense. I think this thing somehow factors. Okay, I'm actually not seeing it anymore. C squared. If I look at their solution, no. Then they get that the derivative they were somehow able to evaluate this, which I'm not really seeing. How do you evaluate this? Find the real part of this. Man. Yeah, okay, I don't know. I think this problem is just really bad, but yeah, so you have to evaluate this somehow. And you end up getting that this is some nice thing in terms of cosines and sines, the real part of this. I think it's very hard to come up with. Anyways, I think that wraps it up for today. Obviously, so I'm going to be live again on Saturday at the same time, 5 p.m. Pacific time. Yeah, so hope to see you all there. And hope this was at least somewhat entertaining. All right, bye.